Hello everyone, it's Steve with Aptera Owners Club. Just a few hours ago, Aptera released a battery update. Very exciting. There is a lot to unpack here. I just spent like over an hour with one of our community members from the Discord community who happens to be an electrical engineer, and we went over this video together. He didn't want to be credited, but he'll be graduating with his bachelor's degree in engineering tomorrow, so congratulations to him. And I learned a lot by talking to him. And let's go through this video together.
Hey everyone, it's Luke here from Aptera Motors Battery Team.
Okay, it's Luke. Remember, Luke was in one of the first videos that Aptera released, and he's still there, and he's the lead of the battery systems now.
I just wanted to let you know we recently achieved a milestone. We're finishing up.
All right, so this is not the 40 kilowatt battery pack. This is the configuration of the 100 kilowatt battery pack. So this is not how the 40 kilowatt battery pack will be configured. It doesn't go up behind the seat. The 25, 40, and 60 kilowatts, they run underneath the seat along the floor pan. And only the 100 kilowatt requires this part that goes up behind the seat.
Our production intent battery design for our launch vehicles. These vehicles.
All right, so this is the bottom of the battery pack, I think, and this is where the flat ends of the battery pack go. And I believe they're using end cooling with a plate along the bottom, kind of like how Lucid runs their battery pack. I see a lot of similarities between the Aptera battery pack and the Lucid battery pack, which I think is good because I think the Lucid battery pack is pretty awesome.
Vehicles are going to have a 41 kilowatt hour battery pack.
I think that they labeled these batteries, so the engineer that I talked to thought that these were colored this way to show which are in parallel and which are in series. So I think they are in parallel this way.
And I wanted to take you through some of the technologies and have
I believe that's the BMS.
you hear from some of the people who are enabling this to happen. So first, you might wonder how we determined how large of a battery pack we need for our design for Aptera.
Okay, so if you look at this, you can see this is the pan that they're putting the modules in, and you see that there's space for 6 modules in this pan. 1, 2, 3, 4, 5, 6. So there's 6 modules. So this is the 40 kilowatt pan.
Our production vehicles will ship with 6 battery modules, just like this behind me, linked together with our patent pending.
So I think this is one module right here. So they're kind of a little bit rectangular, but not really long. And so this is 1, 2, 3, 4, and as you scroll through the video, you'll see all 6.
Busbar design. We have 2,496 cells in the whole pack, 416.
Okay, 2,496 cells. Okay, that's going to be an important number.
16 cells per module.
Okay, he said 416 cells per module. So 6 modules of 416 cells. At this point, I was trying to figure out what their parallel and series configuration is. And I think after talking to people that, do you remember the Lucid battery pack? They had 22 modules, so theirs was long like this, and each module was 42 volts, and they put them all together and they get to a 924 volt system. So basically each module in their system is fully parallel, and they just hook up all the modules in series to get to their final vehicle voltage rate. And I'm told that all the cars do that, and it's because it makes them need fewer BMSs, so it's a little bit cheaper to do it that way. It's more cost efficient. So it's likely that Aptera's 6 modules are all connected in series. If that's the case, then they're probably running a, let's see here. They're probably running, so they have 400, oh, let's see here, let me go here. They have 416 cells per module, right? Module. And that is probably they're running a 16S 26P. So that's going to be their module. And then they run this six. They run 6 modules in series. So if that's the case, then let's see here. So then that's 16 times 6. That's 96. So that means then they're running 96S 26P as their full battery pack. And that equals 2496 cells. Right, so I'm pretty sure that that's what's happening with these guys.
And 41 kilowatt hours of usable energy.
Hello, my name's Ahmed, and
All right, so 41 kilowatt hours of usable energy. We'll revisit that and see what the actual pack capacity probably is.
I'm a battery systems engineer. So Aptera's battery pack is unique in that it is a lot slimmer than most other battery packs. Our main design.
So if you look at this, this is what makes me think that they're using end cooling. There's not enough space here. The cells are packed very tightly together, just like in the Lucid packs. So Tesla currently uses side cooling, although they're going to move to end cooling with their new cells, their fatter cells. But they have a little coil that runs in between their cells. But there's no space to run coolant between these cells. They're packed very tightly together. So I think they're end cooled, just like the Lucid batteries.
Ethos for our pack was efficiency. The pack consists of 6 modules and the power distribution unit.
I think this is showing how things are evolving. This was the bottom plate that held the cells in place. And I think it used to look like this. If you remember from this is the old Kirsten Dunst video that we talked about. And you see these hexagonal things. I think this was the old one. And the newer ones look more like this.
Usually those are separate things, but in our vehicle,
so I think that's
for
their
the sake of
old thing.
Efficiency and space, we like to put those things together.
Hi, I'm Daniel. I'm Aptera's battery integration engineer. I make sure that everything that's happening in the virtual world is working out when we do our prototyping. I think one of the more exciting next steps with the battery is to see how the solar.
So see, this is their new, I think this is their more updated design here. And this looks like they're using epoxy. He's mixing 2-part epoxy to kind of glue it together.
Charging integrates into our battery pack because that's what makes it so special.
So my name is Ryan Caxinat. I am the lead DRE, design release engineer for the battery pack and battery team.
All right, so this is, I went through this with the engineer, and this is the distribution hub. And I think that these are to the these big ones. So the batteries connect to here at the bottom, and then these are buses that will go to the motors probably, and then these are the buses that go to various things like the AC compressor and the solar modules. And so if you look, if we kind of step backward here. You can see that there's a big one here, as well as some smaller ones here. So there's probably I think there's gonna be a port for each motor, so 1, 2, and 3, and then a charge port in the back. And then these go to the various solar modules, AC compressor and stuff, the smaller loads. So my guess, and the guess of the engineer I talked to, is that you will be able to likely upgrade to all-wheel drive later on, because I believe that this is going to stay the same throughout all modules, and there will be a port for the third rear motor. And if you just get a motor and the wiring harness that attaches this port, you could make it an all-wheel drive. Likely. I doubt that they're making a different distribution module for the front wheel drive and a totally separate one for the all-wheel drive. I bet that they're using the same one and just not using one of the ports that would go to the rear motor.
And battery team, I'm going to be working on releasing all of the
right
parts for production, the whole pack for production. the design has been stripped down of all of the unnecessary.
Again, you see here, there's no space for side cooling. And you can see this is the little ends that we saw at the very beginning. And here's their bus bars. It looks very similar. So I think they're doing the exact same thing that that Lucid is doing, is having these bus bars and then welding both all at the top end, the anode and the cathode, welding to the bus bars.
Components, and we're delivering the subsystems that will make it the most efficient pack in the market, and at the same time will perform for long-term durability.
My name is Scott, and I'm the lead battery test engineer. There is cooling and electrical connections and many parts, mechanical parts, that we've taken a slightly different approach to how it goes together and assembles, and we're constantly improving that.
All right, so this is a very important frame here. I'm going to step back because this is our first shot at the actual battery pack that they're using. And at this point, I think we can be relatively certain that this is the cell they're going to use because they're pretty far into it. If you look here, it says INR 21700-50G. So that's very clear to see that. And there's a green one here, which I think is also the same kind. If you remember from this video, this was a video that I made several months ago. 170 is like 24,000 cubic millimeters. And that is a difference of about 50%. So just the 3 millimeters and the 5 millimeters, the okay, so at that point, I was guessing that this was the thing they were using, because in the video, you couldn't see the very last end, the 50E, but it turns out I think it's the 50G. And that's very important because now we can look at the data sheet and know exactly what we're dealing with. So this is a basically a 4.9 amp hour cell with a nominal voltage of 3.63, and then has an end charge of 4.2, and has an internal resistance of 14, and a weight of 70 grams. So by that, we can kind of figure out a couple of things. We can figure out how much the pack weighs, not including all its structural parts, but just the cells. So if you look at just the cells, that's 2496 times 70 grams. So that's 175 kilograms. So 175 times 2.2 for people who use imperial units, that's about 385 pounds. 385 pounds. So it's going to weigh a little more than that because of all the structural units on the side. But most of the weight is going to be the cells. So we know about how much the pack weighs. It's going to be about that much. So with all the structural parts, maybe a little over 400 pounds. And then lots of interesting things we can figure out with this. You can figure out the maximum charge rate of this thing. So the maximum charge rate, since we know that, since we kind of figured out that this is running 26P, you can figure out that, hold on, if it's 26P and each max current is 4.85 amps, so it's 26 cells in parallel, and each one can take a maximum charge of 4.85. This is the maximum charge rate. It can charge at 126 amps. All right, and so if you look at, let's see here. If you look at this thing from ChargePoint, this is like a ChargePoint DC fast charger. So this is a 50 kilowatt charger or a 62 kilowatt charger. If you look at the amps, it's 125 amps at 480 volts. We know that Aptera is using a 400 volt system. So 400 volts at 125 amps, so times 400, that equals 50 kilowatts. So it's running So the fastest that this battery pack will charge is 50 kilowatts. So it won't charge at like 300 kilowatts like the Lucid Air will. The maximum charge of these cells will be 50 kilowatts, which is pretty fast, which is way faster than you need, probably for a pack this size. All right, the other thing that you can figure out is based on its internal resistance. So the internal resistance of this thing is 14 milliamp hours. So you can figure out when you're charging at max capacity at this 50 kilowatt hours, how much heat is this thing going to generate based on its internal resistance. So let's figure that out. Okay, I'm going to erase all this. I should have picked a bigger eraser, sorry. Okay, so from physics, we remember that power, okay, well, I'm going to put it to this. Power equals current squared times resistance. So we know the current is 4.85 squared, and the resistance is 14 milliohms, so 0.014. Okay, so this is how much heat it'll generate while it's charging at max capacity. 4.85 squared times 0.0. Okay, so 0.33 watts. So it's a 0.33 watts. Then if you multiply that times 2496, you get 822 watts. So during charging, okay, my handwriting is terrible. The battery pack is going to take 822 watts during the charge. All right, so then what we need to figure out is during a 30-minute fast charging cycle, how much will the battery pack heat up at that wattage? So if you look at this, I found this that gives you the specific heat of a battery pack. So a battery pack of a 2170 cell has a specific heat of 0.85 joules per gram per degree Kelvin. And degree Kelvin is the same as a degree Celsius. The scale is the same. 1 Kelvin moves up and down the same as 1 Celsius. Kelvin just adds 273 because it starts at absolute zero. But this is basically, this is the amount of joules per gram per degree Celsius. All right, so we know that the battery pack is 174,000 grams. Okay, and then the specific heat is 0.85 joules per gram Celsius. All right, and so we know that if we go 822 in watts is actually joules per second, and then times 60 seconds in a minute times 30 minutes equals, and this will give you how many joules of heat we're going to make. All right, so let's do it. 822 times 60 times 30. All right, 1.5 million joules. So 1.5 million joules. And so with this size battery pack, how many joules does it take to move each degree Celsius? All right, so we do 174,000 times 0.85. If you do this, the grams will cancel and you'll get joules per Celsius. So it's 147, so 148,000 joules per Celsius. So let's see, 148,000 joules per Celsius. So if you divide this by this, you'll know how many degrees you'll go up. So 1.5 million divided by 148,000. If you do that, the joules cancel and you're left with Celsius, 10 degrees Celsius. So that's your answer. With this battery pack, if a 30-minute fast charging will increase the temperature of your battery pack by about 10 degrees Celsius, which is pretty good. It's really good. If you so you're basically you're generating about 1.5 million joules in a 30-minute fast charge with this. We did the calculation for a Tesla Model 3. The Tesla Model 3 charges about 3 times faster because their cells can take on charge about 3 times faster. But the heat generated is about 10 times more. So it's 3 times faster charging at 10 times more waste heat. So they have to dissipate a lot more heat. This is very low amount of heat dissipation on the fast charging. So I think that makes me feel better about the ability of the cooling system to handle it during the fast charge. It just needs to reduce the pack temperature by about 10 degrees during over 30 minutes. I think that's fairly doable.
Constantly improving that for a mass production.
I'm Tom. I'm a design engineer on the battery team at Aptera. Yeah, my main work for the past couple months at least has been these cell carrier parts you see in the back. Those are going to be injection molded. These are 3D printed prototypes in the back. And so the design has evolved quite a bit over time to account for mold flow and creating a large, dimensionally stable part that is lightweight.
Yeah, so I think that's an important thing is that they're gonna, although this is not a structural battery pack, because it's going to be encased in the structural composite body and the cooling belly pan. They are making, the way that it's designed is kind of like a waffle composite with a top plate and a bottom plate and the batteries in the middle. So it is going to be structurally fairly strong.
Then getting a design that uses as little material as possible.
My name is Diego, and I am a battery frame design engineer. Recently, we have been able to finally procure and prototype with our production intent modules, and we also have a production intent battery frame on the way.
So next comes validation.
I think that's great news. It looks like we're getting this news kind of late. They've had a production intent module and a production intent frame designed a while back. So they've already sent that design out to their suppliers, and their suppliers are supplying them that part for validation. So they're a little bit more ahead of the curve than we think.
Certification, and everything that's required before you can legally sell it on the road. As far as certification, that includes lots of charging and discharging of batteries, some safety components of testing. We need to make sure they're certified to be able to ship around the United States. And we need to make sure that everything in the battery pack is sourceable and works well together.
Again, this is their new design of the bottom of the plate, and here's the sides of the plate. So if you make this, they're probably, what they're going to do is this thing at the bottom is going to be the cooling plate. They're going to glue this to the cooling plate with some kind of thermally conductive glue. And then the cooling plate will be here, and then there'll be a top plate, and this thing will be very structurally rigid.
So for our 41 kilowatt hour battery pack,
oh yeah, so we didn't do that calculation. You can see how much capacity there is. So these batteries have a 4.85 amp hour capacity, and they have a nominal voltage of 3.63. So that means that each one is 17.6 kilowatt hours times 2496. That means that their battery pack's about 44 kilowatt hours. So 44 kilowatt hours, and they're using 41 kilowatt hours. So they have about 3 kilowatt hours of overhead in the battery pack.
We approached it from an efficiency first perspective. So we're trying to get the least amount of weight possible, the most amount of energy, while still being safe and cost efficient. We have 20% more energy density at the pack level than some leading brands that you might know. One way we can show you how efficient we are is by comparing to a gas vehicle. Now, for our vehicle, the battery...
Oh, this reminds me. So if you look at this, when they did the testing of these battery packs, they're rated at 1,000 cycles before they lose 80% of their standard capacity. So if you look at 41 kilowatt hours, that should give you about 410 miles at 100 kilowatt hours. Then you discharge that 1,000 times. That means you're going to drive an Aptera 410,000 miles before it loses 80% of its capacity, before it goes down to 80% of its capacity. This is an amount of miles that almost no one's going to put on their car. And we also know from Tesla's own data on their cars that their cars do much better. So EVs do much better than would be calculated by the cell capacity, because this cell capacity is based on full discharge and recharge, and that's not what happens in most people. Most people, they keep their car more in the middle of the charge cycle, which is better. And also the discharge and charging rate during use of an actual car is not the full cycling that they do when they test these cells. So this is a very conservative estimate. It's likely that it's actually about 50% better than this, because Tesla's batteries run about 50% better than their rated cell capacity would say in real life testing. So it's possible that an Aptera will give you 600,000 miles with these cells before it goes down to 80% of its original capacity, which is really good.
Our battery pack is equivalent to 1.2 gallons of gasoline. So imagine going to the pump and filling up 1.2 gallons into your vehicle and then traveling 400 miles. It's pretty mind-blowing.
Yeah, so it's like 360 mpge.
Right. And we think this technology is going to take us pretty far. Our entire team is super excited to build some of the most efficient, energy-dense battery packs in the EV space. And we are looking forward to starting limited production later this year. Thanks for watching.
Okay, awesome. So that was a very exciting video from Aptera. There was a lot to unpack, and I think we figured out a lot of things, which is pretty cool. And a lot of this is speculation, obviously. It's just me guessing and just taking our best guesses as to what these things mean. But I feel like after talking to our friend who's an engineer and things, that these guesses are pretty good guesses. And it's good that they are already getting their production intent prototypes from their suppliers and testing them right now. So we're mid-May, and it seems like they have the battery pretty much figured out, and then they have the suspension pretty much figured out. I think their body's pretty much figured out. They need to figure out their cooling. They're working on their solar modules. So I think the timeline is still pretty aggressive and tight, but things are looking pretty good overall. All right. Well, thanks you for watching, everyone. And I also want to, of course, recognize our sponsors. Enoch, Brian, and Jaron are the 100 kilowatt, and then Curtis, Jeremy, Tom, Dean, Go Climb a Rock, Adimchi, Neil, John, Don, Paul, Harry, and Paulry are 40 kilowatt hours. These guys are supporting us, as well as the 25 kilowatt hour people, and I really appreciate all their support, and I appreciate all of you guys' support by watching and commenting, and really enjoy reading all your comments on the video and interacting with you guys. And yeah, join us on the Discord channel. Lots of cool people there. A community member there helped me analyze this video. It's really helpful. I learned a lot. And yeah, you guys should join us. Links in the description below. Have a great weekend, everyone.